Hey everyone! In this video, we're going to be talking about related rates. Specifically what that means is related rates of change. So just to start off with and to explain a little bit about what these are, related rates of change are rates of change that are directly tied to each other. So for example, let's think about a circle. As I increase the radius of that circle, the area of the circle also increases. So those two rates of change are directly tied to each other. As the radius increases, the area increases. So at a specific moment in time, I could think about how fast is the radius growing at this moment, and how is that related to how fast the area is growing at that same time. So let's talk through this just by looking at an example. So my example here says a golfer hits a ball into a pond of still water, causing a circular ripple. If the radius of the circle increases at the constant rate of 0.5 meters per second, how fast is the area of the circle increasing when the radius of the ripple is 2 meters? So the first thing here is we need to decide on what sort of equation we're going to use. Taking a look at all the information we're given, the question is asking how fast is the area increasing in relation to the radius. So an equation that relates the area of a circle to the radius is just our area formula. So the area is equal to pi r squared. Okay, so now I can define my variables like this, and then the other thing I need to think about are my derivatives. Those are our rates of change. So I need two of them. So I have the rate of change for the radius, so how fast the radius is changing in relation to time. And I also have the rate of change for the area, so how fast the area is changing in relation to time. So in related rate problems, we often think about our variables as a function of time. So as time progresses, we can think about how the radius is changing and how the area is changing. So let's see what we already know. So we are given that the constant rate of change for the radius is 0.5 meters per second. So my derivative of the radius with respect to time is equal to 0.5 meters per second. The other thing I'm given is that the radius is going to be 2 meters. So that is the moment in time when we want to figure out what our rate of change for the area is. Okay, so now that we have everything defined, we know what we want to solve for. It's asking how fast is the area of the circle increasing. So we want to solve for the derivative of our area. So let's go back to our original equation. We decided we're going to use the formula for area of a circle. First step, we're going to differentiate this entire equation with respect to time. So the derivative of capital A, we have the derivative of the area with respect to time. And on the other side of the equal sign, we'll take the derivative of this. So power rule, the 2 comes down. So we end up with 2 pi times r times the derivative of the radius with respect to time. After taking the derivative, we can plug in what we know. I know I want to solve for the derivative of the area, so that's going to stay as is. We want to find out what's happening when the radius is 2, so we'll plug that in. And we also know that dr over dt, this is equal to 0.5. Now if I just do a little bit of simplifying here, we have 2 times 2 times a half. So that is just equal to 2, and we have our pi. So that means that roughly, if I round this a little bit, our area is increasing at a rate about 6.28 meters squared per second. So again, related rates are rates of change that are directly tied to each other. So as we saw in this example, our rate of change for our radius is having a direct impact on the rate of change of the area. So the process, we decide on an equation to use, one that relates our two variables, in this case area and radius. We differentiate that equation, we plug in what we know, and then we can solve for that unknown rate of change.